Okay, so in this video I'm going to talk about homotopy equivalence. Okay, so okay, so suppose we've got a continuous map from space X to space Y, and so a homotopy inverse for F is a continuous map G in the opposite direction such that a G composed with F is homotopic to the identity map of X, and F composed with G is homotopic to the identity map of Y. Okay, so of course here we do G composed with F, that goes from X to Y and then back to X, and so it's meaningful for that to be homotopic to the identity on X, and similarly F composed with G, that's going from Y to X and then back to Y. Or just in the last video we introduced this this category, the homotopy category, H-top, and it's immediate to see that these conditions are just saying that if we work in the homotopy category and we compose the homotopy classes G and F, so we're just saying that we've got these equations in the category H-top. So we're just saying that square bracket G is an inverse for square bracket F, the homotopy class of F, in the category H-top. And we say that F is a homotopy equivalence if such G exists, which is the same as saying square bracket F is an isomorphism in the category H-top. In any category, an isomorphism is a morphism that has an inverse in this kind of sense. So here we're saying square bracket G is an inverse square bracket F in H-top. So that's just saying that square brackets and F is an isomorphism in H-top. Okay, so that's what I mean, and we say X and Y are homotopy equivalent if such an H exists, so such an F exists. And so you say that two spaces are homotopy equivalent if and only if there exists a homotopy equivalence between them. So one very basic type of example, of course, is homeomorphism. If F from X to Y is a homeomorphism, then there exists G from Y to X with G composed with F just equal to the identity, and F composed with G equal to the identity on Y. So that's what it means to be a homeomorphism, and then certainly G composed with F is, if it's equal, then it's certainly homotopic. F is a homotopy equivalence. Okay, so homeomorphic spaces are certainly homotopy equivalent. Most basic example, at least a basic example of the more general situation. Let's look at spheres. Okay, so so we can define a map J from the n sphere to the deleted n+1 dimensional space. Remember, this Sn is just the vectors of length 1 in Rn+1, and vector of length 1 is certainly non-zero. So we can just do the inclusion map, more or less, basically just the identity, but taking the domain to be Sn, the codomain to be R of the n+1 less 0. And we define a map R in the opposite direction. Just to be the usual kind of normalization map, where we just divide by the norm of x, and that's kind of okay. Right. Domain here is Rn+1 with 0 removed, so x here is supposed to be an element of this space. It's a non-zero vector, not non-zero norm. It's admissible to divide by the norm there. So if we start over in Sn, then we've got R of j of x is R of x, which is x divided by the norm of x, but x is in Sn, so the norm of x is 1, so this is just x. So we take R composed with j, then that's just the identity on our space Sn. But the map J composed map in the opposite direction, J composed R, that's not the identity, so we need to do a little bit more work. So we define H as going to map from 0, 1 across Rn+1 less 0 to Rn+1 less 0. By h of t comma x is just going to be x times the norm of x to the power minus t. And so doing this, this is t is greater than or equal to 0, and norm x is strictly bigger than 0, so this kind of power is meaningful here. Okay, then h of naught x is x times. So h0 is giving you the identity, and h of 1x is so that's just j of r of x. So j composed with R is homotopic to the identity on the space here. So J and R are homotopy inverses for each other. And so these are homotopy equivalences. So we see that the punctured Euclidean space is a homotopy equivalent to a sphere. Another sort of example that won't justify in detail, but so a space like this, maybe with some bits sticking off, and y in a space like this with some different kind of bits sticking off. Then x is homotopy equivalent to y. Okay, so I won't write detailed proof of that, but I mean the main point, right, is that these kind of sticky off bits, we can shrink them down to 0, pull them back into the main body of the space, and then if you just look at the middle part here, the circle, the line through it, then that's homeomorphic to kind of the middle part of y. and based on that, you can cook up explicit homotopy equivalence between them. But I'll leave more details of that as an exercise. Okay. Next, I want to talk about contractions. And so by a contraction of x to a point a and x is a continuous map h from 0, 1 cross x to x with h of 1x is x and h of 0x is a for all x. Okay. In other words, h is a homotopy between the identity on x and the constant map CA. If x is convex, so remember what convex means. So this is a typical convex space here. Has the property that any line segment with two ends lying in your space x, then the whole line segment is contained within x. Then so if x is convex, then we can just choose any and then we just put h of t x is be 1 minus ta plus tx. Then so then here's your point x here, and then you're just moving in a straight line from x to a, and you stay within the space x because x is assumed to be convex, and this gives you a contraction. Actually, we didn't quite need it to be convex for this. You needed to just convex means that any line segment stays within the thing, but you could just say it with line segments that end at A, right? You could have like a star shape with A in the middle, it would still work, but we'll just say convex for the time being. Okay, so that gives you a contraction. But on the other hand, spaces like S1 and S2 are not contractible. And so how do we know this, right? I mean, if you just try and imagine what a contraction of S1 or S2 would look like, you can probably convince yourself that no such thing exists. In order to kind of pull every point on the circle round to a single base point, you would sort of have to tear the circle in the middle somewhere, and so it wouldn't be continuous. We don't yet actually have any way to prove that S1 and S2 are not contractible. That's kind of a key thing that we'll achieve by constructing homology theory, but at least you can, it's an example you can be aware of, even if we can't prove it yet. Okay, so we gave a separate definition for contractibility, but it's actually just equivalent to something that we've discussed previously. This shows in this proposition, X is contractible if and only if it is homotopy equivalent to the one-point space and so of course any two one-point spaces are essentially the same. It's typical that we'll write one meaning a one-point space, and the space that the single point is you can call it 0. it doesn't really matter what it is. And the proof, so suppose we have a homotopy equivalence. In other words, a map f from x to 1 with homotopy inverse G from 1 to x. Okay, so we have a homotopy H from G composed with F to the identity on X. And so let's just put A, right? So we've got this map G from 1. 1 means the single is a set just containing 0. So we define G of 0, that's an element of X. Yeah, and then for any X and X, well, we've got well, f of x has got to be f of x has got to be 0, right? I mean, f is a map from x to this one point set, so f of x just has to be the only point that it can be, which is 0. And so G composed with f of x is G of 0 equals A. In other words, G composed with f is just the constant map CA, and H is homotopy from CA to the identity on X, i.e. a contraction. Okay, so now we've proved it one way round. We proved that if X is homotopy equivalent to a single point, then it's contractible, and the converse. Let's just say it's similar. You're basically just using the same ideas. Okay, just a couple more points to discuss about homotopy equivalence. First one is observation here. So let's write it this way. So the identities of homotopy equivalence, and then so if you've got f is a homotopy equivalence and the inverse is a homotopy inverse is some g in the opposite direction, then G is also a homotopy equivalence with homotopy inverse just being F. And thirdly, if and so if you've got two homotopy equivalences, then you can just compose them, and that's still a homotopy equivalence. And the proof that's to say F is a homotopy equivalence if and only if the square bracket F is an iso in the category H top, and the corresponding facts hold for isomorphisms in any category. And we proved that in the section of the notes on category theory. And as a corollary of that, X is homotopy equivalent to X. Then if X is homotopy equivalent to Y, then Y is homotopy equivalent to X. And thirdly, if X is homotopy equivalent to Y and Y to Z, then X is homotopy equivalent to Z. So again, this is all kind of nothing particularly special about homotopy theory. This is all just stuff that works in any category. So we've got that. Just one more thing, we want to talk about compatibility with products. Let's suppose that X naught is homotopy equivalent to Y naught, and X1 is homotopy equivalent to Y1. Then the claim is that X0 cross X1 is homotopy equivalent to Y0 cross Y1. And then the proof we just define, we've got we need to choose homotopy equivalences, Fi from Xi to Yi, with homotopy inverse Gi, say, from Yi to Xi. Then and then we choose homotopies, Hi from Gi composed Fi to the identity, and Ki from Fi composed with Gi to the identity. And then we put f of x0, x1 is f0 of x0, f1 of x1, g of y0, y1 is g0 of y0, g1 of y1. So now you've got x0 cross x1. Your maps f and g going in this sort of direction like this. Okay, and now we need homotopies. So again, we just fit together the homotopies we've already got in an obvious way. So you put h of t, comma x0, x1 is h0 of t, x0, h1 of t, x1, and k of t, y0, y1 is k0 of t, y0, k1 of t, y1, and we check that these give homotopies. G composed with F is the identity, and F composed with G is the identity. Okay, so so being homotopy equivalent, it's an equivalence relation, as we proved on the last screen, and is also compatible with products.